Data Science for Developers with Matthew Renze.
The Azure DevOps podcast is a show for developers and DevOps professionals shipping software using Microsoft technologies. Each show brings you hard-hitting interviews with industry experts, innovating better methods, and sharing success stories. Listen on to learn how to increase quality, ship quickly, and operate well. And now your host, Jeffrey Palermo.
Hello, welcome back. I'm your host, Jeffrey Palermo. Remember, you can go to www.azuredevops.show to see past episodes and show notes, and make sure to go there. There's a lot of great topics, a lot of great interviews, a few announcements that we've announced before. I finished my latest book, .NET DevOps for Azure, and you can go to aka.ms/.NET DevOps book to see that. We launched it at the Build Conference, and it's making its way to Amazon. You can get the preview edition right now. It'll be on Amazon shortly. And also, we have a project that goes along with it. You can go to bit.ly/.NET DevOps project. This is a public Azure DevOps services project that you can use. You can copy and do with it what you will, and it is walked through and highlighted throughout the book. And so my guest today is Matthew Renze. Matthew Renze is a data science consultant, author, and public speaker. Over the past 2 decades, he's taught over 200,000 developers and IT professionals how to make better decisions with data science. His clients include small software startups to Fortune 100 companies across the globe. He's a Microsoft MVP, an ASPInsider, an author for Pluralsight, and an open source software contributor. His focus includes artificial intelligence, machine learning, and data science. Matthew, welcome to the show. How are you?
Very good. Thanks for having me.
Man, I'm really excited to get into this because these topics, these are actually specialized applications, but at the same time, they're so new. And there's a lot of listeners are probably wondering what the heck this is. But before we get into it, a lot of people have seen your courses on Pluralsight. 200,000 people out there have done that. But for those maybe just getting to know you, what can you tell us about your journey? How'd you end up focusing on this stuff?
Well, I started out as a software developer, essentially working on projects that were what we'd call big data now, before big data was a thing, where we essentially had to ship hard drives through the mail like once a month in order to update data sets. And I kept working on projects and working for companies that had large amounts of data and were trying to do something new or unique with it, essentially trying to make better decisions or assist people with making better decisions. And through these various companies I worked at, I learned a lot about software development and kind of, I don't want to say peaked as a software developer, but I got as far as I could without going back to college. So I went back to college a second time, and then I ended up getting double degrees in computer science and philosophy with a minor in economics.
Oh, wow.
And my focus was on artificial intelligence and machine learning. So when I got out of college, I started consulting. And right around that same time, I started hearing a bit of buzz about this term data science. And the more I learned about it, the more I was like, wow, this is exactly what I've been trying to do this whole time, but it just didn't have a title to kind of capture the essence of what it is I was trying to do. So I ended up rebranding or taking some time to rebrand as a data science consultant, and then went into that space for a while, essentially using my knowledge of computer programming, data, and then the data science stuff I was learning in college to essentially help people make better decisions with data science. And then I also began leveraging machine learning right around the same time it started to really explode in the industry. But there was not enough people that really understood it for it to be highly valuable. So there wasn't a lot of opportunities at that point in time to do like consulting on machine learning projects. So I ended up starting to do a lot of machine learning stuff on the side while I was also doing the data science consulting, and eventually got to the point where I understood the concepts well enough to teach courses on it. So I started teaching. Eventually, I started creating some courses for Pluralsight on the topic. And now, essentially, I travel the world. I speak at conferences on data science, machine learning, artificial intelligence. I build little projects to help companies figure out how these technologies could be applied to solve a problem. I go in and consult with the companies to help them solve problems in this way. and create courses that essentially teach people how to leverage these technologies to either make better decisions, to automate decision-making processes, or to solve a problem that no one has ever encountered before, and we now have the technology to solve.
Nice. Well, that's awesome. It sounds like you're one of the few top tier experts in this space. It's such a new space, but it's growing by leaps and bounds.
Yeah. It's actually just, I mean, for me, it seems like it's been around for a while. And half the time when I go and give a presentation, I feel like, oh, this is all old news and stuff. But then I give that talk and everyone's like, oh my God, like I didn't know anything about any of this stuff. And like, this is huge. This is going to change our whole industry. And I'm like, yeah, I know. That's why I essentially bet my career on it and shifted from doing software development to doing data science instead. But it took quite a bit of time and effort in order to get up to speed on the new technologies and techniques and patterns and practices. And I had to go back and learn quite a bit more statistics in order to feel confident with what I was doing as a consultant. Yeah. But the one thing I really want to get across to software developers is that there is a lot of stuff you can apply data science to now that doesn't require a PhD in statistics or a PhD in data science. There's just a lot we can be doing that's either prepackaged and ready to go, or doesn't require such an in-depth knowledge of the complex math and statistics that it's outside of your reach.
Well, that's good to hear, because there's been there's some demos for certain products where it's like, oh, look, magic, click, 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 you're done. But let's get into what it really is. I think developers are probably really familiar with reports, data warehouse, star schemas, denormalization, and the business intelligence of dimensions and facts and aggregates, and that's all normal. So what's the overview? What the heck is data science, and how does it take what may be normal database stuff, and what new things are there that we need to be aware of?
Well, data science is really, it's a combination of things. It's a process that you're using in order to create knowledge that you can use to make intelligent, rational decisions. And it's also a mindset, a way of thinking about the world from a skeptical point of view, that you then propose hypotheses, and then you test those hypotheses using empirical evidence from the data that we're collecting, and then make decisions based upon evidence either in support or against those hypotheses. So it's essentially the application of the scientific method to the world of business, but supercharged with all of this massive amount of data that we now have access to. So if you think back to a scientist doing science, even a couple decades ago, it was really expensive to gather and collect data. You would essentially have to create experiments, run surveys, all of these things that costed quite a bit of, quite a bit in terms of time and energy. And now the data is just all around us, and we just need to figure out where to find it and then how to transform it into something that can be used to add support either for or against a hypothesis. So we can now take our entire business and we can work with it in a data-driven decision-making approach, rather than the old ways of trying to make decisions, which largely rely on a lot of human bias, a lot of guesswork, estimation, and in some cases, somebody thumping their chest in order to, show that they're right and everyone else is wrong. So there are now better ways to make these decisions, and that's really where data science is making huge strides in the world of business.
So it sounds like for data science, you're not just using the data that maybe your software generated, but you're going and grabbing additional data sets and pulling them in?
Potentially. So most people start with the basics, which is just, getting their application to start logging data that could be useful in order to answer questions. But as you kind of grow and evolve as a data science organization, you'll typically start adding in third-party data sets that provide valuable information when joined with the data sets that you have. And at some point in time, you even get a bit further where you might start running your own experiments and essentially generating new data that never existed before in order to answer a specific question. But it's usually a step-by-step process where you kind of evolve as an organization to get to the point where you're doing full-blown data science. But you have to start somewhere.
Yeah, I've heard of car dealerships using baby birth rates in certain areas, or housing starts, in order to kind of predict a certain number of years from those big bulges, in order to determine, okay, well, these people that are there now, some number of years from now, they're going to be of ideal car buying age. And so we need to have that area covered to expect this demand. Is that one of these scenarios?
I've heard of something like that. I don't know how much truth there is to it, but those are the kind of things that we're doing with data science that were not possible just a few years ago. For example, one of the classic examples is that, well, actually, a few that you might find interesting. We now know that beer and diapers are frequently sold together from an old OSCO data analysis that they did years ago. So some people apparently started putting the beer next to the diapers in order to increase the likelihood of impulse purchases.
Wow.
We also now know that the sales of strawberry Pop-Tarts increased sevenfold right before a hurricane makes landfall.
Wow.
So now they actually ship out truckloads of Pop-Tarts.
Oh, wait a minute. Doesn't every shelf of everything clear out when a hurricane's coming?
Pop-Tarts more so. You would essentially run out of Pop-Tarts unless you actually brought a bunch of them in order to meet the increased demand. Because if it's a sevenfold increase, they're going off the shelf like hotcakes.
Yikes.
And we also know a bit more concerning, and this is where things start to get a bit scary with the data science knowledge. Purchasing certain products together like unscented lotions, extra large bags of cotton balls, and mineral supplements of certain type strong indicators that a person is pregnant.
Ooh.
So there's actually online retailers, or not online, but retailers that can predict with a relatively accurate time window when you're likely to give birth.
Gotcha. Wow.
And if you can get injected into someone's buying habits when they have a major life transition, like having a child, it's hugely influential for the rest of that person's like retail shopping experience. Like if they can lock you in at that point in time, they pretty much have you for life as a customer.
Right. Okay. So I can see how that would be helpful in commerce because, of course, you're trying to sell stuff. But so many applications are either internal for their employees or B2B of nature. The application isn't designed to sell stuff. So you mentioned one thing, which is logging certain things. So why don't we start at the beginning of the process? So if someone has some software, concretely, what should they start doing to even prepare themselves to be able to do some cooler new stuff?
Well, here's a couple of real world examples for software developers. Imagine that you're trying to build a web page for the company, and there's an argument going on as to whether the color scheme should be this bright blue versus everyone else thinks it should be this green color, and so you can't make a decision as a team as to whether you should go with the blue theme or go with the green theme. So something you could do is essentially run an A/B test on the website. Essentially, you just randomly redirect 50% of the users to the blue page and randomly redirect 50% of the users to the green page and see if it actually, one or the other actually increases the click-through rate. And if you see a statistically significant increase in the click-through rate, you know that one color is actually preferred by the users over the other, and you should then go with that color. So essentially helping them make a simple decision, or I should say it's a simple decision, but has profound impact because click-through is crucial for a website to actually, function and draw in users. Another example might be if you have a feature that you're trying to build. Feature A and feature B do roughly the same thing, so you don't want to build both versions of the feature since they're solving the same problem in two very different ways. So you might just survey a couple of your users in order to see which feature that they actually prefer. So rather than having to go and build both features, you could essentially get just enough information to find a statistically significant difference between feature A versus feature B in terms of the user preferences, and then just build one instead of the other, or instead of having to build both. So another way to solve a simple, concrete problem with data science. But then we can get quite a bit more complex, and this is where it becomes a bit more difficult to discuss the scenarios. For example, say you're trying to build an application that has to be able to, what's a good example? Predict whether there's a product in the picture or not. So say you work for a cola manufacturer and you just need to find photos on Instagram that contain your soda.
Okay.
So you can essentially write a machine learning algorithm and train it to detect that image. And this is actually quite easy to do now. Just a couple of years ago, this would have taken a whole data science team to pull it off. Now it's essentially a couple lines of code and a couple of images that you upload into an Azure like image recognition service. And you can then scan pictures all over your company's Instagram account to find those pictures that actually contain that product that you're looking for. So,
okay, now you just started to throw out machine learning, but we've been talking about data science. So what's the difference and how do these fit together? Is one an umbrella category? Which one's more specific?
So data science is a more general kind of concept, whereas machine learning gets a bit more specific. So most people would consider machine learning to be a subset of the data science space. It's essentially using a set of algorithms in order to predict some kind of outcome, which if you think about data science in a more general sense, data science is essentially trying to make better decisions with data. And so machine learning is essentially trying to have a machine predict those decisions or make those decisions, with human beings essentially just providing it with a data in order to train it to make those decisions. And then once you've trained it, it essentially makes those decisions or predictions or finds those patterns automatically. So if you're training it to training it to detect, or let's see. So in a simple example, if you're trying to help it learn whether to approve or reject a loan based upon a customer's financial history, you could essentially just feed it the data of everyone we've approved for loans based on their history and everyone we've rejected for loans based on their history, or even better, the people that have repaid their loans in full based on their history and the people that have defaulted on their loans based on their history. And then show it all of that data, and it will essentially learn how to predict whether a person should be approved or rejected based on the likelihood that they will successfully pay back the loan or default, with nothing more than that data. So a human being no longer has to make that decision automatically. However, it's important to still have human beings in this loop because we don't just want the machines taking over and doing all of this stuff on their own. So there's definitely some caveats to that. But ultimately, you can teach the machine in order to make the decision in the same way a human being would do, using a scientific process and method in order to make sure it's sound, rational decision making. And then beyond that, rather than just using tabular data, we can do the same kinds of things now with technology called deep learning. So deep learning is a specific type of machine learning that allows us to detect much more complex patterns in data. So that's where you could take a photograph, showed a few images of your product, and then it would be able to find that product in all of the photos on Instagram or Snapchat or wherever you're looking for the photos. I guess Snapchat's not it.
Yeah. I actually haven't done a whole lot with Snapchat.
Yeah.
I've heard it's a thing.
I'm out of date too with that kind of stuff.
The Azure DevOps podcast is sponsored by ClearMeasure, a software engineering firm and Microsoft Gold partner, empowering development teams to be their best. ClearMeasure equips developers with the DevOps tools, methods, and automation necessary to focus on building their applications, rather than wrestling with builds, deployments, or environments. Click clear-measure.com to see whether a DevOps implementation is for you.
Okay, so if we could maybe hone in on something that the listeners could take away and do today. They're already working with some type of Visual Studio software, and they're already, let's say they're building and testing and deploying it's running in Azure. Let's pick a scenario and just to kind of get them concrete. What could they do today with what's available?
So, for example, with Visual Studio, they have code quality metrics built into the Visual Studio. I think professional, but I'm not sure. It might actually just be an enterprise yet. So what you can do is you can essentially analyze your code base using static code analysis, and you get certain measures of code quality. So say, for example, you go into your software reviews, and every time someone's like, yeah, this code's just not good, but they can't explain why. Mm-hmm. And you're like, no, I think that's actually written well. So now you could have these discussions using objective measures of code quality instead. So use your static code analysis to get measures like cyclomatic complexity, maintainability index, inheritance steps, all of these things that either make code simple or complex, or good code versus bad code, if you will. And so rather than having essentially discussions that are all based on emotion and feel about code, you can now have more objective, rational conversations about these. Like say, well, this code or this way of doing the code has a much lower cyclomatic complexity versus this way of doing it, which has a much higher cyclomatic complexity. So simply using Visual Studio and the code base as a source, a data source, you can start to answer some of these questions and make some of these decisions using the data that exists inside of the code itself. And then beyond that, you could go to the Azure DevOps and start using its repository of information in order to make more advanced decisions, like looking at things like check-in frequency. How frequently are we checking in our code files? In general, teams that check in frequently have higher performance. And so if you start analyzing a trend that we're just not checking in that often and we're starting to have a bunch of problems, well, maybe part of the problem is we're just not checking in frequently enough. Other things like changes in terms of the code complexity over time. So if you do static code analysis temporally, you can start to detect things like the maintainability index increased over time. And if things are growing exponentially, you're not going to make it to the end of the project because the complexity will get so large that by the time you're approaching the end of the project, no one will be able to write any new code without breaking 10 other things. So being able to look at the entire DevOps process, as not just a factory to build software, but a repository for data that you can use to help you make better decisions about software development practices, and a laboratory you can use in order to run experiments in order to figure out, well, are certain things working better or worse than others? Like, for example, have we actually seen an increase in the velocity of our agile software development practices ever since we switched over to pair programming, or has it actually slowed us down? Most people would have no idea, but now if you're actually using the information in your DevOps pipeline in order to answer these questions, you're essentially implementing or taking a data science mindset to solving these kinds of problems and answering these questions.
Okay, so specifically, if people were to do that, would they need to design their own data repository, SQL Server schema? What does that database look like?
Well, most of this data is already being tracked automatically by the Azure DevOps, and you should be able to access that through an API and pull out the information as needed. But in many cases, you may actually need to build something in order to collect more data. So, for example, telemetry data is kind of iffy. Some people would build their own custom repository for all of the telemetry data from software running in real time in production. Or you could use something like application insights in order to automate the collection of this data to help you make decisions about users, the users interacting with your software in real time, and to make decisions that will help improve the overall user experience for your users.
Okay, so if we're pulling out data from the APIs, we need a place to put it. We might be able to put it in application insights, or what are the other common choices? Obviously not an Excel spreadsheet, right?
It depends. So in some cases, something as simple as an Excel spreadsheet is good enough. Like if you're doing just a back of the napkin kind of experiment and you just need to collect some data and do a quick analysis, Excel's perfect for that. When you get a bit more advanced, you'll start working with applications like I use Python quite a bit for data science and machine learning, and I also use a programming language called R. So R is essentially a statistical programming language designed specifically, for data science by statisticians and data scientists. And so either of these programs work really well for doing everything from basic to more advanced kinds of data analysis. And then once you get to the point where you've got a whole lot of data that you're working with, that's where you need to start considering things like SQL Server or going into the big data platforms like Hadoop and Spark. But most people are probably not going to be getting into that space very soon. If you're listening to this podcast and you're interested in just getting started, you're going to want to start with the basics and work your way up to that point eventually. But if you are already working with Hadoop and you're working with R as a server and stuff like that, you're probably not finding a lot of value from this podcast right now.
Okay,
because you know most of the stuff already.
So is it just a further progression beyond, say, the Kimball methods of star schemas and data warehousing, or is it would you consider it totally something different in parallel? Is it an enhancement to the stuff we've already done in data warehousing, or is it just a quantum leap and it's different?
Well, I think there's two camps right now. There's the Kimball style data warehouse camp, and there's the big data repository camp. And there's also a camp that's kind of playing together where they essentially create a data lake using the big data technologies. And then for the data that needs to be available quickly for ad hoc analyses, they essentially load that into the Kimball style data warehouse for the analysts. But you can always go back to that data lake to rebuild the data warehouse or to answer one-off questions that are done in more of a batch operation style.
So can you help sort out all these words? We have lake,
okay.
We have warehouse,
yep.
We have mart. What's the difference?
So let's see, where do I start? So, all right, you've got raw data, which is essentially just the text files coming in from your logging application, your images coming in from your photo application, any raw information you store in some kind of repository. Now, that's unorganized data, so you could query it, but it's very difficult to query it unless you write a program to essentially look at every file and pull out exactly the information you need, aggregate it, and then answer the question and do all the data cleanup in the process. So a data lake is essentially a large repository of information that's been structured in some way to make it easier to answer questions of the data. So it's not just in completely raw format. It's essentially either in like a Parquet file format or some kind of file format optimized for distributed computing of very large data sets.
So that would imply a certain product being used for that?
Potentially. So depending upon what you're doing, you might use like a Cosmo DB kind of thing, or you might use something like Spark, or one of the Hadoop kind of flavors of the day. And this is all changing as we speak. And the term data lake right now is a pretty nebulous thing. Some people mean it more just unstructured data, and other people mean sort of structured, and other people have a much more rigid structure idea in mind. Okay. But then you can answer questions of this repository of data, but it's typically done in very large, bulky operations. So you're not just like typing in a quick query and getting an answer. You're essentially building a script of some kind to pull the data from the various sources and then answer it. But it's still way faster than building a custom application to answer a question with the raw data. So then beyond that, you've got a data warehouse. And a data warehouse specifically is data that's organized in a very specific format we know as the star schema. That's Kimball's idea of how a data warehouse should be built anyways. So the star schema essentially stores everything as measures and dimensions. And that makes it really easy to ask a question of the data and do so in a very fast way. So you can ask, write a query, it gives you an answer pretty much immediately, and then you go on to your next question. So you can rapidly iterate through a decision-making process or a data analysis with the data warehouse.
And all the BI tools are designed to go against star schema SQL Server databases, right?
Yep.
With Tableau, Power BI, everything, even Excel, Power Pivot, they're sort of expecting a Kimball type structure, aren't they?
Yep. Yeah, that's the best way to work with the data from a BI perspective, from all of my years of experience with this stuff. You can still do the same things with a simple text file of data, but if you have things stored in a star schema, it's just way easier to answer questions because the data has essentially been cleaned up. It's been organized in a way that makes it really easy to answer questions. And all of your column names are human readable. They essentially make sense to the end user trying to ask the question. And then beyond that, we have data marts, which are typically a subset of a data warehouse for a very specific department or a very a more specialized group of people. So it might actually have conventions that apply just to them, but don't apply to the company as a whole in terms of like their naming, the way things are organized and whatnot. But that kind of gets you across the spectrum of the I guess, big data repositories and the data warehousing tools and technologies.
Okay. And so it sounds like as we get into more machine learning, we're consuming more of the data lake style repositories that's not been cleaned up and structured that specifically?
Well, that's the part that's still being figured out as an industry. There's a lot of people that essentially want to replace the concept of a data warehouse with a big data repository that is structured and can essentially answer questions as quickly as a Kimball-style data warehouse. The technology is rapidly evolving, but some people in the relational database world think, no, the relational database is going to just catch up and it will essentially be able to outperform these big data tools at their own game, essentially. Mm-hmm. So I'm still uncertain how this is going to pan out. There clearly is value to tools like Spark and Hadoop, and there's clearly value to Kimball-style data warehouses. But my guess is that at some point in time, one's going to win out, and the other is going to kind of become more of a relic, antiquated to more specific use cases.
Yeah, and from a build and deployment perspective, there's kind of a rift here with anything that is a SQL Server schema, which data warehouse, data mart, that could be a SQL Server schema. The DevOps story is already written for that because it's just a SQL Server database. We know how to deploy those. But then the other parts that are newer, and you mentioned R and Python and the structure of the data, the listeners are grasping. They're probably thinking, okay, what does a DevOps pipeline look like for that? What does it mean to build that? What does it mean to deploy that?
Yeah, that's actually an interesting question. So essentially, deploying databases has always been a bit difficult, or the more difficult part of the DevOps process for me. The way changes are merged and stuff is just different than the way code changes are merged, because as data is changing, it's just more difficult to keep things in the proper order without everything falling apart. So when you get to big data DevOps pipelines, I have to be honest, like I've actually never worked on a big ops dev pipeline. So I don't actually know how you solve some of these specific problems that you'll run into. Doing it with a data warehouse, I've been in that case, and it's just you take all of the issues you run into with doing a normal like a normalized database deployment for a transactional application, and you just kind of scale up the difficulty proportional to the size of the data that you're dealing with. So it's way easier to deploy a transactional database for a production, transactional system than it is to deploy a data warehouse for, a data analysis system.
Right. Okay. So where does AI fit in now with this whole picture?
So as we're moving further forward, essentially, I think what we're going to see is that the data science space is going to evolve to data-driven artificial intelligence. Right now, almost all of the most impressive breakthroughs in the AI space have been from machine learning, which is essentially data science combined with a subset of pattern detection in artificial intelligence. So I think what you're going to see is a lot of capabilities for applications in the very near future that make it possible to do things that we could not do just a few years ago in a much easier way. So, for example, let's see, what's the easiest way to describe this? So we've got a technology right now called reinforcement learning, which when we apply deep learning to reinforcement learning, we get what's called deep reinforcement learning. And right now we're using this technology in order to essentially play video games. So some people may have seen this already on the internet, where you've got a computer that learns how to play something like Pong or Pitfall or any 8-bit video game, or now we're getting to 16-bit video games as well too. It learns how to play that video game without any human instruction. All they do is show it the pixels of the screen as input. They give it its score, which is its reward signal, and then it knows that it can move left, right, up, down, or press the A or B button. So that's all the information the system has, and then it just is allowed to explore with the goal of optimizing its score. So when you let these algorithms run over time, they essentially learn the physics of the game in a sense that it knows that if I move the paddle underneath the ball, it will eventually bounce off the ball and I score a point. So it keeps doing those kind of things based simply on the information it's receiving. So after several iterations, a couple hundred iterations, these algorithms essentially learn how to play these video games as well as a human being, and sometimes way better than any human being because they've got quicker reflexes and there's certain things that make them better. But there, at no point in time has a human written any code in order to solve this video game or to beat this video game. Essentially, it's just the algorithm learning from the simulation, the data that the simulation or simulated environment is producing. So in the very near future, it looks like we're going to have a lot of simulated environments for specific problems that we're dealing with, whether that's in robotics or the knowledge work domain. And essentially these agents, these deep reinforcement learning agents or AI agents, will essentially learn how to solve these problems on their own without a human being actually having to write the code. Because in the old days, we would essentially have to solve each problem by saying, if this, then this, and work our way through the problem that way. But in the future, it's more likely that we're going to be teaching the machines how to solve the problems just by giving them the constraints and then providing them with the data in order to solve the problem, or a simulated environment that produces data in order to allow them to solve the problem. And then, everything from, the food industry, fast food, we'll be able to make automated burger flippers without having to explicitly program them, robots to build stuff. For knowledge work and scenarios, we've got portfolio management, there's logistics, there's a whole slew of applications to this once we get over this next hurdle, which is probably going to happen in the very near future. Now, there's a huge difference between what we call narrow AI and general AI. And narrow AI is essentially using this artificial intelligence technology to solve a very narrow specific problem, like flipping a burger or something like that. But general AI is the kind of the end goal where we've got agents that are essentially able to solve problems in a very wide domain and in a very flexible way. But that's still probably several years away. But right now, using these narrow AI technologies, especially with the emergence of things like deep learning and deep reinforcement learning, will probably become way more mainstream, and software developers that are either looking for a career change or to stay relevant as things are changing around them will probably want to get invested in these technologies pretty soon.
So this is what I see. You tell me if I'm wrong. And I guess I'm on the early 20 something years of my career. But when I started, the web was oh, wow. What's the web? Oh, you have internet? You have an email address, that kind of thing. And software went from mainframe to desktop. And then we've had a huge thing of desktop to the web. And there's a whole generation of developers who they only did desktop and they kind of never transitioned to the web. And I'm talking about people who probably did a whole bunch of COBOL and then maybe did some Delphi and then maybe some, VB desktop, C++. And the web is a whole other generation. And then now we have a whole generation that did web, and some of them have done mobile. And it seems like this may be just the whole nother generation where it's not just, hey, use a little bit different library or tool or IDE, but this is a whole different paradigm shift of thinking and which type of patterns may be applicable.
Absolutely.
Is that the level of shift?
That's what I think is happening. There's still always going to be room for general purpose programming, at least until we figure out a way to automate, AIs to actually write code on our behalf. But the set of problems you'll solve with machine learning will increase and take over a lot of things that you may have had to try doing with explicit programming. And the types of problems we'll be able to solve with computers will increase as well too. And that will be because of technologies like machine learning, deep learning, reinforcement learning. And I think in the future, software developers are more going to, instead of like plugging together libraries and essentially making libraries of code play together, we'll probably be spending a lot of our time essentially wiring together little AI modules that this one detects whether your product's in there. This one detects the sentiment of the tweet that the person put. Now this one, essentially decides whether this is a potential customer or not. Now this one essentially tries to figure out what that customer's buying habits are. And this one then sends them an advertisement through their Facebook account specifically targeted towards their preferences because we think they'll potentially be a new user of our soda product or whatever. So essentially combining these various little AI modules together, machine learning modules, I think that's going to be a lot of what we're going to be doing in the next generation.
Well, it's an exciting time, that's for sure. And I'm excited to be a part of it. Any resources that our listeners should look up, any websites, go-to places to learn more about what we just talked about briefly?
Well, I'd have to say the first place I'd recommend going to is my website for obvious reasons.
Heck yeah.
I have quite a bit of information. I have a whole series of online courses that teach the basics of data science, some machine learning, and deep learning as well too. And I'm working on a course series right now on essentially trying to take software developers from the basics of data science through machine learning, through deep learning, and then to data-driven AI. It's probably going to take me a couple of years to finish this up, but the first courses are beginning to come out now. So stay tuned to my website for more. And there's tons of great information available all over the internet. I've got an article or two about getting started in data science that you might find interesting. We can feel free to put that in the show notes or something, but there's plenty of resources available to get started now. Okay.
And your website is?
MatthewRenze.com.
RENZE.com. Okay.
That's correct.
Awesome.
So you can learn more information by visiting my website, MatthewRenze.com, or you can also search for my courses online at Pluralsight, or you can find me on various places on the internet, including Twitter, on LinkedIn, and elsewhere.
Awesome. Well, thanks so much, Matthew, for being with me. This is a great bit of information.
Thank you. Thank you for having me.
And until next time, keep shipping.
You've been listening to the Azure DevOps Podcast, a show for developers and DevOps professionals shipping software using Microsoft technologies. Go to www.azuredevops.show for show notes and other episodes. On behalf of your host, Jeffrey Palermo, and our sponsors, thanks for listening, and may God bless you.